Okay, so let's start our lecture today. So, um, yeah, so we want to use the M test to set up a sum of upper bound for the log function. Okay, so um, uh, yeah, I think I did similar stuff before, right? So, uh, so so uh, yeah. So let me check my notes. Mm. Oh, okay. So okay. So uh, yeah. So this is by the uh, so using Taylor expansion. Expansion of the log of 1 minus z over omega j at yeah, just use the Taylor expansion of this function. So yeah, so we know that wait. Yeah, so this is equal to let's see. So first we plug in z equal to 0, right? So we get 0, and then we take the first derivative, and then we get yeah. So 1 minus when we get 0, and then we take the derivative. Okay, so it is just negative 1 over omega j. Yeah, I think I did the computation before about the first derivative. So let me check. Yeah. Yeah, so I'll just yeah, so this is not 1 over the derivative is 1 over that, and then this is z over omega j, and then yeah, so minus z square over 2 omega j squared. Okay, and then minus so minus z squared over 3 omega j cubed. Sorry, z cubed over 3 omega j cubed. Okay, minus da da da. Okay, so therefore, yeah. So therefore, so we have that the log, right? So therefore the L of no. So therefore the modulus of the capital log of 1 minus z over omega j plus z over omega j plus z squared over 2 omega j squared. So which is equal to the modulus of negative so wait, log of 1 minus u, which is equal to that, and then u will be screen small, u is okay, so which is equal to z cubed over 3 omega j cubed minus okay, so here there's a formula that I used. So I used the formula where the Taylor expansion of the log of 1 plus, sorry, the capital log of 1 minus u is equal to yeah, so what I used is that I used the formula so the capital log of 1 minus u. Okay. So and also when the modulus u is less than 1. Okay. Shoot. So when modulus u is less than 1, so we have log of 1 minus u, which is equal to negative summation k from 1 to infinity u to the k's power over k. Okay, so we use this formula, right? And then here plug in u to be z over omega j. We have that, okay. And then for this omega j, when we add like the first two terms, right? So the first two term is being cancelled out. So what's left is just the third term. So so it's just the sum, which is equal to the sum of negative of the sum k from 3 to infinity of so in this case u is just this guy, right? Z over omega j. So let's say z to the k's power over omega j to the k's power. So this is uk over k. So this is the k here. Okay, so Okay, so oh, okay. So okay, so we showed before that this guy is actually shoot. Wait a minute. So okay, because here this z is actually in k prime, right? So so if z is in k prime, then how does this work though? So wait. So 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 when okay, so what I'm concerned is that because here this k prime is being enlarged, right? So so what we have is that okay, so okay, so yeah, I need more space. Okay, so let me just erase this part. Okay. So originally, so we have okay, so because this factor n naught is the number I picked. Yeah, so this n naught basically is the index I pick, such that we have that n naught we pick such that for n bigger than n naught, this lattice point omega j actually lies outside a disk of radius 2r, right? So originally we have that. So when n is bigger than n naught, the modulus of omega n is bigger than 2r, right? Yes. So this is what we have in the past. Okay. So now, okay. So now, so okay. So now pick. Since this omega n, the lattice point, they go to infinity, right? So I can pick, let's say n1, okay. N1, such that when this n is bigger than this n1, we have the modulus of this will be small n. Okay, so the modulus of omega n is bigger than. So I want to use this guy, right? So I want to use. Wait, does this help? Let's see. So when modulus of omega n is bigger than 2 times this radius, right? Okay. Okay, so let's see what do we really want to set up here. So, okay, so let's see. So what worked in the past? So what worked in the past is that okay. So for modulus u less than 1/2, we have so this L of u. So L of u is a notation for yeah. So what is the notation for L of u? So yeah. So L of u, which is equal to the log of 1 minus u plus u plus u squared over 2. Okay, so essentially just replace this z or omega j by u, and then this whole thing inside the bracket basically is just L of u. So the modulus of L of u, which is equal to yeah, so which is equal to the sum of k from 3 to infinity of uk over k. Okay, which is less than equal to the sum k from 3 to infinity of modulus u to the k's power over 3, over k, which is less than 1/3. Yeah, so 1/3 times k from 3 to infinity of modulus u to the k's power. Okay. Yeah, because the case for k bigger than 3, right? So this guy, this 1/k is strictly less than 1/3. Okay, so so then we use the equation for the geometric sums. So this is equal to modulus u cubed over 3 times 1 minus modulus u, which is less than equal to okay, so which is equal to less than equal to 2/3 modulus u cubed. Okay, so yeah, so we have this inequality in the past. Okay, so so right now I think what we do is that we just pick yeah, so we just let r prime to be equal to 3r/2, right? So we just replace the original radius that we used in the past, and then we replace it by a new radius, which is r prime, and then so this is equal to bigger than like 2r prime. So okay, so then so this implies then we have that okay, so then for let's see n for capital N bigger than let's say the maximum, because I also want this n to be bigger than this n naught in order for this L n naught z to be well defined. Yeah, because I want to show that this L n naught, I think it does better, but for some technicality, I think I want to show this L n naught z actually converges to this L of upper n naught z. Okay, so I want this n to be at least bigger than this n naught. So the maximum of this n naught, comma n1. Okay. So then we know that so then so we have z over omega n modulus of z over omega n is so shoot. Yeah, so let me say it this way. So then for z in k prime and actually for any z in k prime, and also n, let me use j. Okay, so j bigger than n, we have the modulus of z over omega j is less than equal to r prime over 2r prime, right? Okay, so therefore, okay, so this implies that this little L of z over omega j modulus, which is less than or equal to this guy 3 over 2 over 3 2 over 3 modulus u cubed, which is equal to modulus of z cubed over omega j cubed. So then, which is less than or equal to 2 over 3. So z basically can be bounded by this r prime cube, right? R prime cube, and then over modulus of omega j cubed. Okay, so now this we have the factor omega j cubed. Okay, so now we can just reproduce the previous argument. So now, so this is the this is the uniform upper bound. Sorry, this is the upper bound for the modulus of this guy, right? So this is less than or equal to 2 over 3 times r prime cubed over modulus of omega j cubed. Okay, so then let me add one thing. So because so let me add a condition. So for z in k prime and also j bigger than this n. Okay. Okay, so this implies that so this implies that by the M test, okay, and the convergence of the sum of j bigger than this capital N of 1 over modulus of omega j cubed. Okay. We have that this L of yeah, so we have our result, right? Yeah, so here I shouldn't use this. So here I double use the index n. So what am I gonna use? So maybe I'll use n prime for this n. Okay. And j bigger than n prime. So L n prime n converges uniformly to L of Okay, so converges uniformly to L of n. Sorry, L of n naught. On K prime. Okay. Okay. So yeah, because again for the previous few terms, there's only finite terms for the tails, right? For the head term, we can just take the supremum, and then for the tail terms, we use this bounds, and then we know that this bounds is summable, and supremum is a finite number, so they add up to finite. So okay, so we do have this condition right now, right? Yeah, and also by the uniqueness of the limit, right? So they must be the same as this L and naught. The limit of this guy must be the same as L and naught by the uniqueness of the limit. So so that finished the proof of this one. So, and then this implies what? So it's finished here. So so this implies that okay, so since L n naught upper n okay, so is holomorphic on the disk. Okay, so so uniform and it converges. Okay. And yeah, so let me use the family of the function, right? So n bigger than n naught. Okay, it's homomorphic on the disk, and K prime is arbitrary and compact. So therefore, by the convergence theorem for the homomorphic functions, so we have that this L n naught z is homomorphic on this disk, right? Okay, so since okay, I want to keep this definition. So so maybe I'll use here. So yeah, so actually yeah, so here so this is what I just wrote here. Okay, so let me just continue here. Since R is arbitrary, so we have shoot. Wait. Okay, so I showed last time that this I think this sigma z is well defined, right? Yeah. So okay. So maybe let me use this one. Okay. So yeah. So this LZ I think is this L naught z. Okay. I think I add the notation n naught later. So this one should be L naught z. So and then okay. So this implies that okay, because I'm using this Ln naught z to define this sigma k z, right? So therefore, since this Ln naught z is holomorphic, so e to the Ln naught z is also holomorphic, and also the product of holomorphic function is also holomorphic. So therefore, so this implies that this sigma k z, okay, is holomorphic. Okay, not on K, but I just showed that it is on like a larger disk. Wait. Okay, yeah. So, yeah, so this R is sort of because I picked this R. So remember originally I picked the K first, okay. And then I define the sigma KZ according to this compact set K, right? So remember that because in the very beginning we let R to be the supremum over the modulus of Z, where Z is in K. And then based on this R, and then we define like n naught, such that when this n is bigger than n naught, the modulus of omega n is bigger than 2R, right? And from there we define like this Ln naught nz to be this function. So and then yeah, so everything at the beginning is just depends on this K, right? So now we show that we show that this guy so is homomorphic on this function, so on this disk, right? So okay, so this implies that okay, so this implies that sigma z is holomorphic on K. Okay. Okay. And then since K is arbitrary, okay. Okay, so this implies that sigma z is entire, okay. Okay, so this finishes the proof of our sigma function. Okay, so I'll continue next time for the rest.